Earthquakes release blistering heat that can melt rock in an instant. When the ground trembles during an earthquake, we experience only a fraction of the true energy being unleashed beneath our feet. New experiments from MIT geologists reveal that most of an earthquake's energy doesn't go into shaking cities or fracturing rocks. It is instead released as searing heat, hot enough to melt solid rock into glass in the blink of an eye. In a laboratory tucked away at MIT, researchers have been recreating miniature earthquakes, or lab quakes, to explore what really happens when the Earth's crust suddenly slips. These scaled-down quakes are triggered in carefully controlled settings using powdered granite samples subjected to stresses similar to those found 10-20 kilometers beneath the surface. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. The results are striking. Less than 10% of a quake's total energy produces the seismic waves that ripple through the crust and reach us as ground shaking. Even less, under 1%, goes into breaking rocks apart and forming new fracture surfaces. The lion's share, roughly 80%, is converted directly into heat. In some cases, this flash of frictional heating was so intense that the granite briefly liquefied, forming tiny veins of glass-like melt. We were able to watch rock surfaces go from room temperature to 1,200 degrees Celsius in microseconds, explains Daniel Ortega Arroyo, a graduate student in MIT's Department of Earth, Atmospheric and Planetary Sciences. That's enough to melt solid granite instantly, and then it cools just as quickly when the motion stops. This heat budget tells a bigger story. Earthquakes are not simply sudden slips along faults, they are the release of stress that has built up over millions of years as tectonic plates grind against each other. The way this energy partitions between shaking, heating, and fracturing depends on the history of the rocks themselves. Faults that have slipped many times before may dissipate energy differently than relatively fresh rocks, making some regions more vulnerable to destructive earthquakes. The deformation history, the memory of the rock, dictates a lot about how it fails, Ortega Arroyo says. That history can influence whether an earthquake unleashes more shaking, more fracturing, or more heating. To reach these insights, MIT researchers compressed granite samples between pistons while embedding magnetic particles that acted as microscopic thermometers. When the samples slipped, sometimes by only a hair's breadth, their rapid heating altered the magnetic fields of these particles, recording the temperatures reached during each lab quake. Custom-built piezoelectric sensors captured the shaking, while microscopes revealed how the grains fractured. Together, these measurements provided the most complete energy budget of a quake ever assembled. What they discovered mirrors the violent yet hidden processes of natural earthquakes. Although we feel the shaking most acutely, it is the blistering underground heat that dominates the quake's physics. In large-scale earthquakes, this invisible furnace could alter fault rocks, weaken them, or even change how future quakes unfold. Unlike the weather, where we can observe and measure daily changes, it's nearly impossible to monitor the deep earth directly, says Matej Peck, MIT geophysicist and senior author. Lab quakes allow us to isolate the physics at very small scales and then extrapolate to what happens during natural, kilometer-scale ruptures. This new understanding could sharpen seismic hazard models. If geologists know how a region's rocks behaved during past quakes, whether they primarily fractured, heated, or shook, they may be able to estimate how the same fault will behave in the future. That knowledge could one day improve earthquake preparedness in some of the world's most seismically vulnerable zones. As Peck puts it, our experiments give one of the most complete pictures yet of the physics of earthquake ruptures. By learning how rocks behave under extreme stress, we're taking steps toward better forecasting and hazard mitigation. The Earth's crust, it seems, is not just a stage for shaking buildings. It is a furnace where heat, stress, and memory combine to shape the quakes of tomorrow.